Okay, so we've had a look at some differential calculus concepts over the last 3 weeks, and we've learnt some of the core arithmetic and the core mathematics behind it. But now we're going to take that knowledge and understanding we've developed about what a derivative is, how we can use calculus to find tangents, normals, that kind of thing, and actually apply it to the real world. And we'll be looking at many different ways we can use calculus, because it's a very powerful form of mathematics. But first off, in this episode, which is going to be a reasonably lengthy episode, we're going to be looking at rates of change, which again, as you can see, will probably link in with your knowledge of calculus at the moment, because you're always thinking of the derivative and whether that is the gradient of a given point or the gradient of a tangent line or the gradient of an entire function represented by another function. But we're going to be looking at specifically populations and things that do have rates of change and some of the more conceptual side behind this. So let's have a look at this question, shall we? The rate of change in a population is given by dp over dt, and this is just like having dy over dx. Instead of x and y, we have p and t, which will be population and time. And this dp over dt equals b lots of 1 take p over h take d over 100 p, where a, b, and d are known constants that represent the birth rate, b, the maximum occupancy of a nation, h, and the death rate, d, and the population is p. Answer the following questions. So if the dp over dt equals 0, what assumptions could we make about the population? Okay, so let's think about it. The dp over dt equals 0. What does that actually mean? Well, it means that for the change in the population, or the change of the population divided by the change in time, there's going to be no difference. Oops, I'll draw that a little straighter. So if that were to be the case, say this was population up here, and this was time, and this was just a graph, it doesn't have any real numerical values, but we wouldn't see any sort of difference. Say it's meant to be a flat line, sorry, but we wouldn't see any sort of difference within the population. That's what the dp over dt means. There's no change for our y and x, so no change for our p and t in this scenario. So let's have a look at our original equation and work out what factors could mean that there is no change involved. So remember, we have 3 different variables. We have p, and, well, p is population, sorry, but on top of that we have b, which is birth, d, which is death, and h, which is the amount of occupancy within the nation. So let's see, to get a 0 change, there are generally people being born and dying all the time, but one way that we could get 0 change is for h to be constant. That means that we're not having any more expansions in the maximum occupancy of the country. B to be constant. And B to be equal to D. That would be one particular scenario. So let me just explain how I got that. Well, if h is constant, then that means that we're basically not having any more maximum occupancy, so this variable, this value within the denominator isn't changing. For b to be constant, that means that there's no change in the number of births, because obviously that would cause a change in the population over change in time. And b equals d, as a third factor of this one assumption, would be that the number of births is equal to the number of deaths. Because remember, if we had more deaths than we had births the other way around, we're going to have some kind of change, positive or negative, in the population over time. So if b equals d, then births and deaths are the same. And if h is constant, then the maximum occupancy is the same. And if b is constant, then d is constant, because they're both the same. So we end up having no change and just a constant thing throughout it. So say the birth rate was 3 and the death rate was 3, then obviously for every birth there would be a death, so it would balance it out. So we could have a go at this. We could basically just substitute in a few values and see whether we can get it so that the dp over dt equals 0. But if we just think about this situation where we have an equal number of birth and death, and we also have no change in the housing requirements, then obviously there would be a constant population. Okay, so let's think of maybe another reason why it could be constant. Well, another reason I can think of is h is still constant. Because remember, if h changes, then, and h obviously has to be greater than 0 because you can obviously need some occupancy, but if h changes, then of course it's going to change the value of dp over dt. So h is constant, b equals 0, and d equals 0. So what does this mean about our population? Well, it means that there's no change in the number of people who can actually live there due to the occupancy. There's no births and no deaths, which is a very utopian idea, but it would not change the population over time because no one's dying, because no one's being born, because there are no more available houses, or there's no change in the number of houses or the population. Then obviously we're going to end up with a nice flat line, a constant population. And that's just a few little ideas there about why we could have some of those assumptions there about, obviously, the values of b, h, and d from the equation. So let's move on to the next question, which asks, if dp over dt is negative, then what assumptions can we make about b and d if h is constant? So again, this is just applying calculus knowledge and rates of change to a real-world application, population, and working out, well, what are the factors involved. It's analysing the mathematics. So, dp over dt is obviously going to be less than 0 then. And because dp over dt is less than 0, that means that we're having a negative value. So it's going to be a negative change. So what assumption could we make about the population of b and d if h is constant? Well, if h is constant, the number of houses is obviously staying the same. So the number of houses is constant, or should I say maximum occupancy is constant, meaning that we're not losing houses, so we can't attribute h as being a factor to a negative change in the population over time. Okay, well, if we had more births than we did deaths, then obviously we would have a positive dp over dt value because the population would be increasing over time. However, because we have a negative one, it must mean that our population is decreasing because we are having more deaths than we are births. So this must mean another contributing factor to this is that the number of deaths, or the death rate, is greater than the birth rate. So there's more people dying than there are being born. And that's how we get a negative change, because the population is decreasing because more people are dying than they are being born. Okay, so that's that question answered. So let's move on to the next one, where the dp of dt is 10, the death rate is 6, and the maximum occupancy is 16,000 within a nation. Our population is 13,000, and we need to be able to find the birth rate. So what we do is we take our original formula and we would rewrite it, dp over dt, and that equals b lots of 1 take, and then we have our population divided by the maximum occupancy, so that's 13,000 over 16,000. And then we have take the death rate, and the death rate would be 6, based on there, so that's 6 over 100 lots of p. And it's always good to use brackets. So now what do? Well, we just need to substitute down, and what we can do here is we can also substitute in our dp over dt value to be 10. So now, let's go through the process. We get 10 equals, and it's 1 take 13,000 over 16,000. So because it's 13,000 over 16,000, it's the same as having 1 take 13 over 16. Now, if we take 13 over 16, we can just imagine this as being, say, 16 over 16. I'll just put that in there for the moment. But if it's take 13 over 16, then we can see that we'd end up with b lots of 3 over 16, because 16 take 13 is going to be equal to 3, and 16 take 16 again. We need the denominators to be the same when we're actually subtracting fractions. So that's how we're able to get that down to 3 over 16. And then here we have take 16 over 100, and I probably should have substituted in p before, but p is equal to 13,000. And so, because that's 13,000 there, and I know I'm sort of writing a bit slanted there, sorry about that, we have 13,000 multiplied, 13,000 over 1 multiplied by 6 over 100, and we're just going to imagine that the result we get from that will be negative, so that equals 13,000 times by 6, so we can do 13 times 6, 3 times 6 is 18, carry the 1 is making it 78,000, and that's all over 100, and we can cross out the zeros, so we get the answer of 780, and we can get rid of that. So now I'm just going to go around to the other side of the board, so hopefully I can write less slanted, and hopefully I don't block too much of the light as well. But now what we do is we simply have 10 equals 3 over 16 lots of b, and then we take 780, so therefore we get 10 plus 780, because again we're moving it to the left-hand side of the equation, so we're inversing the operation, equals 3 over 16b, so therefore 790 equals 3 over 16b, and again we want to be able to get b on its own, so we need to take this from the numerator on that side and put it into the denominator on the left-hand side, the other side. So we get 970 divided by 3 over 16, and hopefully it hasn't gone off the board. In fact, I'll actually rewrite it here. So we get 790 over 3 divided by 16 equals b, and then we're able to use our calculator to get an approximate value for b. So we go and we enter into our calculator as follows: 790, divide symbol, and then we do bracket, open bracket, 3 divided by 16, close bracket, and we get an approximate value of 4,213 and a third. So that means, well, it's actually a equals value there, if it's not an approximate. But from that, we're able to say, well, the birth rate is obviously going to be reasonably high at 4,213 and a third. Okay, so now that we've done that, we may move on to different problems. So I'll go across again to the other side of the board. Sorry about doing that, but as you can see, I'm quite limited for board space because I really like zooming in close. But now what we can do is I can try another problem with a different application of rates of change. So we've gone through population as being the first type of rates of change. Now we can have another one up here. So this one I've kind of got written down the bottom, but it says due to the factors of the global financial crisis and the global food crisis, comma, the cost of cheese has increased over the last few years. So again, we're going to be looking at rates of increase. This can be modelled by C of t equals, and then we have e to the t, where C is the additional cost on top of $1.20, and T is the number of months since the global food crisis. Okay, hopefully that isn't too wonky, and hopefully that didn't take too long, didn't bore you to death. But that's our next problem, so let's have a look at what we're going to be asking here. So, first question regarding this is, what is the dy over dx and its significance? And what is the cost of cheese at t equals 6? So again, not too difficult questions for rate of change. Again, this is just sort of an introduction to being able to apply calculus, but there is a fundamental rule that I'll need to go through here as well. So, what we do first is we just analyse the question and see, well, what are they asking us? And we can see that we got a function of c against t, and it's an exponential function. It's e to the t, and we're able to see that c is the additional cost on top of $1.20, so that's going to be $1.20 plus the increase, and T is the number of months since the global food crisis. So let's assume, and I probably should have put this in the problem as well, but the value of C is going to be in cents as a unit there. Okay, so the derivative of Ct equals e to the t. So what would be the derivative in this case? Well, it would be, obviously, the change in cost. So what does that mean? Well, if we had it at the 2-month mark and we found the gradient there on our function e to the t, well, we'd obviously be finding out the amount that it's going to increase by. So that's going to be the gradient at that given point, the increase in the cost of cheese because of the global food crisis and the global financial crisis. So again, the change in cost, which is going to be our gradient. That was a nice simple question, but now asks us to find the dy over dx. And we need to be able to find the derivative of e to the t, and we just assume that t is like an x value in this respect, because again, t is x in this scenario. So if we have e to the t, there is actually a rule of differentiation for this, and it states that the dy over dx of e to the x, we'll just use x as a notation here so you're able to remember this rule, but the derivative of e to the x is actually e to the x as well. And that's an interesting concept that I'll be going through in a future video, but just this rates of change video, it's just a rule that you can remember. So this means that the increase per given month can be calculated by e to the x. Okay, so again, that's just sort of saying, well, the cost of cheese is going up by this much each month, e to the x, where e is obviously the natural logarithm. So, from this, we're going to go on to our second question, and it asks, what is the cost of cheese at t equals 6? So the cost, again, we have our function, the cost equals e to the t, and again, c is the additional cost, so we need to be able to add $1.20 on top of that. So let's just assume this is for a small block of cheese, obviously. But what we do in our calculators, on our TI-84s or our graphics calculator, if you have a Casio, is you would go second function, and then you'd press the ln button. It'd be e to the x. The ln button can be found next to 4 on the TI. And then when you've got the e in there, you just need to raise it to the number of months since the global food crisis in question. So it's t equals 6, so it's e to the 6, and that's 403.4. So obviously the price of cheese has gone up quite a bit, but we've got to remember that's in a sentence. But still, that's quite a significant amount. Obviously, the global food crisis has significantly affected this. In fact, very significantly. In fact, I probably should have done it as years, but never mind. So what we do now is, again, we just need to be able to put this into dollars. There are 100 cents in a dollar, so we're going to move this back 2 decimal places, and we're going to get $4 free as being the increased cost. But then we need to add that to our additional cost. So in our calculator, we do 4.03, and then we add on the additional cost of $1.20, and then we get that, and we can write a summary. I'll just go around to the other side again in order to save room. But the summary would look something like this. The cost of cheese after t equals 6, so 6 months after global food crisis and financial crisis. I could write that out if I wanted to, but again, I'm sort of running out of space. Is going to be equal to, and then we have $, $5.23. And there we have it, rates of change and application of differential calculus. So again, there will be more videos on this kind of thing. We may look at a few more rates of change. We may look at some physics and motion concepts, because that's another great application of differential calculus. But this is some of the basic questions. Again, you just got to analyze what it's asking you. I'll be going through some of these rules about logarithms and that a bit later in a couple of the other videos. But for now, we've done 2 questions. We looked at population, and we've looked at the global food crisis and financial crisis, so cost. But I guess I'll see you in a future video. Hopefully you enjoyed it. If you have any comments, just put them below. Thank you.